Swayam Prabha. Digital India. Educated India.
Let us start our today's lecture on soil dynamics. We were continuing with our module 5, that is on machine foundations. A quick recap what we have studied in the previous lecture. We have started the theory of elasticity, that is elastic half space theory, use of that for design of machine foundation. Assumption for soil was, it is assumed that the soil is semi-infinite, homogeneous, elastic, isotropic body. And to start with this problem, we had seen that the elastic half space theory have started basically by Lamb in 1904 by considering it as dynamic Boussinesq's problem. In the case of static, we know what is static Boussinesq's problem, to obtain the load below to obtain the stress below any particular load at any depth and also at any radial distance. So, for the dynamic load, it has changed to dynamic Boussinesq's problem. Like for vertical type of vibration, this is the model shown by Lamb, and for horizontal loading, this was the model. Then we have seen that Reasoner in 1936, he established the theoretical basis for studying the response of a footing supported by an elastic half space, and the basic model considered by Reasoner was like this. We have seen the picture of the model, that this is the, for any machine, suppose it is a rotating mass type oscillator, the circular footing with a radius of r naught, at any depth z we can find out its displacement conditions, etc. And total we has considered as elastic half space or elastic body with these are the properties: shear modulus G, Poisson's ratio mu, and rho as the density of the soil. Then the theory of Quinlan and Sang both have given individually in the same year 1953 how to apply Reasoner model of 1936 to compute the vertical displacement below the vertical mode of vibration for any machine foundation. So, this is the expression was given. Z naught is nothing but the vertical displacement, P naught is amplitude of the dynamic load vertically applied, exponential I omega t, where omega is external frequency or the exciting frequency, G is shear modulus of the soil, R naught is equivalent radius of the circular footing, and these two terms F1 plus I F2, F1 and F2 are called as Reasoner's displacement functions, and these Reasoner's displacement functions are nothing but, we have seen these are functions of Poisson's ratio and another term A naught. How A naught was defined? We have seen that also. For vertical vibration, dimensionless frequency factor is called A naught, which is expressed like this, that is omega r naught by Vs, where Vs is the shear wave velocity in the soil media. So, in terms of F, it is 2 pi f r naught by Vs. So, this is non-dimensional frequency factor, and another non-dimensional parameter was defined by Reasoner, that is called mass ratio small b. Mass ratio is expressed like mass of the total machine plus foundation system divided by density of the soil and r naught cube. R naught is the radius of that circular foundation. Then in relation to this, we have seen what are the different expressions available by using theory of elasticity for different modes of vibration by considering rigid circular footing resting on a elastic half space. So, for vertical motion we have seen this is the expression for spring constant k z, that is 4 g r naught by 1 minus mu, mu is Poisson's ratio, g shear modulus and r naught is equivalent radius of circular footing. It is given by Timoshenko and Goodyear in 1951. For horizontal vibration, the expression for k x is this given by Bycroft in 1956. For rocking mode of vibration, the expression for k psi is given by this. It is given originally by Borowiecka in 1943, and for torsional or yawing motion, this is the expression for k theta, the spring constant. Now, if we do not have a circular footing, which is quite common in practice, many a times we have either rectangular footing or the square footing, then we can convert the dimensions of rectangular or square footing to equivalent circular radius. So, how to convert that? Like for translational vibration, the expression is like this. For rocking mode of vibration, R naught is computed using this expression. For yawing mode of vibration, R naught is computed by using this expression, where this C R D are defined like this. 2 C is nothing but width of total width of the foundation. So, C is nothing but half of the width of the foundation, and 2 D is the total length of the foundation. So, D is half of the length of the foundation. And how these expressions were derived? Just for translation mode, area has been equated for a rectangular footing to a circular footing. Then for rocking mode and yawing mode, inertia has been equated corresponding to its axis of rotation. Also, we have seen that for rectangular footing, the expression for spring constant for different modes of vibrations were given by different researchers, but however, it is always better to use the basic expression for circular footing by using the transformation of the dimensions from rectangular to the circular dimensions. And this was the design charts as per the Reisner's model. It is given in Richard 1962 for Poisson's ratio value of 0.25. As we have seen, it is a function of Poisson's ratio. So, for a particular value of Poisson's ratio, how with respect to this non-dimensional frequency factor A naught, the dimensionless amplitude factor where vibration amplitude A z can be computed using this design chart for various values of mass ratio B. And this is for constant force type vibration with Q naught like this, and this design chart is for eccentric mass or rotating mass type of vibration with Q naught is m e omega square with these two rotating mass, and A z can easily be computed using this expression, because in this expression m, e all are known. From design chart A naught we can compute for a calculated value of B. Using this chart we can read this y axis value, and from which you can get the value of A z. So, that is the use of Reisner's model. Also, I have mentioned that either we can directly use the Reisner's model in the previous design chart as we have discussed just now, or we can use this design chart given by Bycroft in 1956, how F1 and F2, these factors, that is Reisner's displacement functions, they vary with respect to this dimensionless frequency ratio A naught and different Poisson's ratio. So, that also we can read from this graph and can use in the expression for computation of Z naught, as I have already mentioned. Then we have started discussing another simplified analog proposed by Leismer in 1965. Leismer analog of 1965, what it does, the Reisner's displacement functions, which was given by small f expressed like f1 and f2, was converted to capital F just by using this multiplication factor, that is 4 by 1 minus mu, that is Poisson's ratio, just to take care of the effect of Poisson's ratio, because earlier we had seen Reisner's displacement functions are function of both Poisson's ratio as well as dimensionless frequency factor. So, to get rid of the Poisson's ratio term, Leismer has modified it to multiply with respect to this expression, so that it is now independent of the Poisson's ratio. It is already taken care of within these factors capital F1 and capital F2. And for different modes of vibration, we have started discussing from the Leismer analog for vertical mode of vibration. Again, the mass ratio has been modified by Leismer, whatever Reisner mass ratio was small b, now here it is capital B. For vertical mode, it is capital Bz, which is expressed by this expression 1 minus mu by 4 m by rho r naught cube. And amplitude of motion can be calculated like this, damping ratio, Cz, Kz all can be calculated using this expression. Once again, we had discussed the expressions for damping ratio for different modes of vibration as per Leismer simplified analog, that is the eta z is the damping ratio for vertical mode of vibration is given by this expression, Bz is that modified mass ratio, eta x for horizontal motion, where Bx is the modified mass ratio for horizontal mode of vibration, eta psi is for rocking motion and eta theta is for torsional motion. So, these are expressions for damping ratio. And for vertical mode of vibration, we have also seen what is the basic equation of motion for using Leismer's analog. It is nothing but similar to our mass spring dashpot model, that is m z double dot plus this is the expression for Cz, that is the damping coefficient for vertical mode of vibration times z dot, and this is our Kz, because we have seen the spring constant for vertical mode of vibration is nothing but 4 g r naught by 1 minus mu times z equals to that externally applied load. And how to calculate the damping ratio, which we have just now seen the expression, this is the way. Cc, the critical damping constant, can be calculated by 2 root over Km, K here is Kz. So, we can use the expression for Kz here, and then if we apply this eta equals to nothing but C by Cc damping ratio, and on simplification we can get this expression. And how to compute the different values of amplitude of oscillator motion, these are the expressions which we will see soon in the design chart. Az for constant mode of vibration and Az for rotating mass type vibration, these are the factors which the design charts are available. So, looking back at the vertical vibration, here a comparison of elastic half space theory, that is basically a Reisner's model, and simplified analog given by Leismer has been compared for different values of dimensionless frequency factor with magnification factor. Magnification factor is nothing but this is our K. So, K is Z by Q naught, okay, for a constant force type vibration. For different values of Bz, it has been found that they are essentially giving almost a good comparison with the exact half space theory. So, that is why instead of using complicated half space model, we can also use Leismer simplified analog for using elastic half space theory for the design purpose of machine foundations. This is again for rotating mass type excitation, how the variations of magnification factor with respect to different values of frequency, dimensionless frequency factor and modified mass ratio Bz that has been expressed. And this was the design chart as I had mentioned. This is for what? This is for resonance condition, that is how to obtain the resonant frequency and the displacement at resonant condition. The previous two cases were for operating frequency condition. Now, for resonant condition, how to use this design chart of Leismer. For vertical mode of vibration, Bz we can easily calculate, because these all parameters are given to us. M is known total mass of the machine plus foundation, rho of the soil is known, density, R naught is known, mu of the soil is also known. So, Bz is known to us. So, y axis value, suppose if it is 2, if we calculate, then depending on what type of dynamic loading we are considering, whether it is a constant force type or a rotating mass type, we can go to that particular graph and drop the line to calculate A naught m. What is A naught m? A naught was nothing but dimensionless frequency ratio, and A naught m is the dimensionless frequency ratio at resonance. So, this value of A naught m will give us the value of resonant frequency. So, if you use the expression of A naught in the A naught m, whatever f you will get finally, that will give you nothing but the resonant frequency for that type of design foundation. Now, how to use this value again for calculation of displacement amplitude at resonant frequency? This is the another chart. Bz again we know, depending on whether it is a constant force type or a rotating mass type. These are the different lines. Constant force type is with m is the magnification factor, this dotted line, and for rotating mass type excitation it is m, that is this solid line. So, knowing the value of Bz, go to that corresponding curve depending on your type of loading, drop it here, you can read the value of or mrm depending on type of loading, put that in this expression, you will get the displacement amplitude. And remember, these displacement amplitudes are nothing but displacement amplitude at resonance condition. Like in mass spring dashpot model also, we have computed displacement amplitude at two conditions, one at operating frequency, another one at resonant condition. So, here also using the first two graphs, we can find out the displacement amplitude in case of operating frequency, and in this case using the last two graphs we can find out the displacement amplitude at resonant frequency condition. Now, let me give you the expression for damping ratio. As for the vertical mode of vibration, already I have given the expression of damping ratio, and how it is obtained I have shown. From the equation of motion, you know the what is your Cz, then you divide it by Cc, Cc you can compute from your Kz, and then ratio of Cz by Cc, you will get the damping ratio. So, in this case, for vertical mode eta z, we have already seen 0.425 by root over Bz is the expression for vertical motion. Then eta x is 0.288 by root over Bx. This is for horizontal vibration. For rocking, eta psi is given by 0.15 times 1 plus B psi root over B psi. This is for rocking motion, and then eta theta is expressed as 0.50 by 1 plus 2 B theta for torsional motion. Okay, fine. So, these are the expressions of damping ratio has to be used for corresponding vibration whatever we are going to analyze. How we can analyze this thing? There are two ways again. Either we can use direct chart of Leismer to get the magnification factors for particular value of A naught, and then do the calculation, or we can use the expression for amplitude of vibration similar to mass spring dashpot model, because equation of motion, the shape of equation of motion is same. So, the solution for the equation also will be same. Is that clear? So, either analytically you can compute, or from reading the graph you can get the result. So, let me tell you how to read the graph from the design charts. So, this is one of the design chart, first design chart I should say, for vertical mode of vibration with rigid circular footing on elastic half space. It gives relationship between mass ratio versus dimensionless frequency at resonance. So, this is at resonance condition. Remember, it is not at operating frequency. Okay? There are different curves, one for at resonance condition, another will be for at operating frequency condition. First, you calculate Bz, knowing the mass of your machine plus foundation you are going to design, the section in the trial which you have taken. So, knowing the mass, rho of the soil you know, R naught you have chosen some dimension for the footing. So, this is known to you, mu of soil Poisson's ratio is known. So, Bz is known to you. How you can use this curve? Bz is known. This dotted line shows the design curve for constant force of vibration, and this solid line shows the design curve for rotating mass type vibration. So, first you calculate this Bz for vertical mode of vibration. Suppose it is coming 2. For if it is a constant load type you are addressing, go to this curve, drop it here, calculate the value of or read the value of A naught m from this chart. Remember, this A naught m is not the same as A naught. Why? A naught you have calculated the dimensionless frequency factor is using your exciting frequency or operating frequency, whereas A naught m is at resonance condition. So, in this way what you are getting from this design chart, you are getting the what is resonance frequency for the machine plus foundation system. Okay? Then what you are doing? Go to the next chart. This is showing the relationship of mass ratio versus magnification factor at resonance. So, again there are two lines, one solid line that is for rotating mass type excitation, the dotted line for constant force type excitation. So, for constant force type excitation we need to use this expression to get the amplitude. For rotating mass type excitation we need to use this expression to get the amplitude. Bz is known to us. Take, suppose it is 2, take it here. If it is rotating mass type, come to this line, drop it here, you will get the value of, for rotating mass type you will get MRM. That value of MRM you put here, ME, E and M are known to you. So, you can easily get what is the amplitude of motion. Is this clear? How we are using this Leismer's design chart for our design purpose? This way whatever displacement amplitude you are getting, what is that amplitude? It is not at operating frequency, it is at resonance condition. Clear? So, for operating frequency you can use the expression as we have used for mass spring dashpot model. Okay? Only thing in that case, the damping ratio value you have to calculate using Leismer analysis, and other expressions for Kz or Bz, everything will be as per Leismer analog. Fine? Okay. Now, let us start today with sliding mode of vibration for Leismer's analog. So, in case of Leismer's analog for sliding vibration, the modified dimensionless mass ratio expression will be Bx, where Bx is given by this expression, and the damping ratio already we have discussed. Let us look back here. Eta x is 0.288. Truly speaking, it is 0.2875, but you can approximate as 0.288, okay, by root over that Bx. And the expression for Kx also we have seen for horizontal mode of vibration. This is the expression for Kx. And how to compute the R naught, that is for translational mode, that also we had discussed earlier. So, this is the expression to compute the R naught if our original foundation is in rectangular shape. Now, how to use the design chart? This is again you can see for different value of B phi with respect to different A naught, the amplitude can be computed, and here the exact solution, that is using elastic half space theory, and the dotted line shows the Leismer's analog. They compare very well. So, it shows that Leismer analog can be used for the design purpose, and this is the way at resonant condition one can find out what are the resonant frequency for a designed foundation section and what are the displacement at resonant condition. This is the expression for Bx, which we can easily compute for the given data. Depending on constant force type or rotating mass type vibration, we can drop it here. We can calculate A naught m. This is your A naught m, that is frequency at resonant condition. Then we will use this design chart, knowing the value of Bx depending on case of whether constant force type or rotating mass type, we will get the magnification factor. Using that in this expression, either of these two, we can get the displacement amplitude at resonance. Now, coming to the rocking or pitching mode of vibration using Leismer's analog, the expression for dimensionless mass ratio for rocking mode of vibration is given like this. B phi is given by this expression, where m naught is nothing but mass moment of inertia in this case. And remember, here it is rho r naught to the power 5, not 3. Okay. Why? Because this mass moment of inertia, whatever unit it will have, to make it non-dimensional, we need to multiply it with respect to r naught to the power 5. So, that it will become kg centimeter square. Here also it will be kg centimeter square. Okay. And how to compute that r naught for rocking mode of vibration? This is the expression. This is the expression to calculate r naught for rocking mode of vibration. For pitching, what will occur? C and D will interchange. C is the dimension in the x axis when we are considering rocking, and D is the dimension in the direction of y axis. So, for pitching it will be 16 d cube C by 3 pi. Now, let us look back here for calculating k phi. This is the expression. C phi also can be calculated like this. How to use the design chart? Again, in the similar way for other two cases. For resonant condition, B psi we can easily calculate for rocking mode of vibration using this expression. And then depending on whether constant force type or rotating mass type, look here, in this case both the cases are giving exactly the same line, only except at this very high value of A naught m. Otherwise, they are essentially a single line. You can get the value of resonant frequency, and then using this chart we can get the value of magnification factor, this m psi m or m psi r m depending on type of excitation from the known value of B psi, and then can calculate this A psi m and for different exciting loads of dynamic load. Coming to yawing mode of vibration using Leismer's analog, this is the expression to calculate the non-dimensional modified mass ratio of Leismer, where J psi is nothing but polar moment of inertia divided by rho r naught cube. And the expression for damping ratio is given by this, expression for spring constant is given by this, and R naught has to be calculated for yawing mode of vibration. This is the correct expression, look at here, this is the expression to calculate the R naught for yawing mode of vibration. So, similar design charts are also available for yawing mode of vibration. So, B theta can be calculated. Here also for constant force type and rotating mass type, curves are essentially same till this value of A naught m, then they slightly vary. You can get the value of A naught m, that is resonant frequency you can calculate, and then using this chart you can get m theta m or m theta r m, from which you will get the value of displacement amplitude at resonance condition depending on what type of excitation we are using. Now, let us come to the application part. Let us do the design checks for block type machine foundation using the concept of this elastic half space theory. So, this is the problem statement. It says a block type machine foundation is designed in such a way that weight of foundation block is WF is 0.25 ton and weight of machine is 0.5 ton, with foundation block area of 75 centimeter by 90 centimeter, and the height of the foundation is 15 centimeter. So, it has already been designed. What we have to do, using elastic half space theory, find out the displacement amplitudes at operating frequency. So, the first we are trying to find out the displacement amplitude at operating frequency only, and what is the operating frequency? It is given as 1500 RPM for these two modes of vibration. First one is vertical mode of vibration and the second one for horizontal mode of vibrations. What are the other data given to us for the design? That consider the amplitude of external dynamic load for both the cases of whether it is vertical mode or horizontal mode. It is 188.64 kg force, and consider the Poisson's ratio of the soil as 0.25. Use 3 different types of soil, that is with G shear modulus as 50 kg per centimeter square, then another type of soil with shear modulus G equals to 100 kg per centimeter square, and the another type of soil with G equals to 200 kg per centimeter square. And what has been asked? Obtain the results for both constant force type excitation and rotating mass type excitation. And for the case of rotating mass type excitation, we need some more input parameters, those are also given, that is, take the eccentricity as 1 millimeter and the eccentric weight is 75 kg force, that is 10% of total of this machine plus foundation system, which is 750 kg force. Now, comparing the previous problem statement, what we have used in case of mass spring dashpot model, are you able to find out what is the basic difference from the given input data from MSD model to EHS theory for the same problem? Because the same design problem we have checked using mass spring dashpot model also. Now, we are going to apply elastic half space theory. What is the basic difference? Can you identify which input data is not given here, but it was given or it was required for mass spring dashpot model? Can you identify? If you compare with the previous problem statement what we have used for mass spring dashpot model. If you look carefully, there is one input parameter which is not given in this EHS theory, or which is not required to be given as an input parameter for EHS theory, whereas that parameter is essential for using mass spring dashpot model. Yes, the parameter is damping ratio. Can you identify? In the case of mass spring dashpot model, we have solved the same problem, exactly same problem we have checked using mass spring dashpot model. There the value of damping ratio should have been given, otherwise we cannot proceed with our design check calculation. Whereas, in case of elastic half space theory, the damping ratio value need not to be given. Why? Because the expression for damping ratio using elastic half space theory are already available, which needs to be used to compute the damping ratio if we are using the elastic half space model. So, this is one important note. So, let us start now solving this problem. In this case, again we need to assume the unit weight of the soil or the density of the soil. We will assume the same as we had considered for the mass spring dashpot model also. That is, for these 3 different types of soil, for G equals to 50 kg per centimeter square, we will assume gamma, that is unit weight, as 1.7 into 10 to the power minus 3 kg force per centimeter cube. I will write it here. So, let us consider for the soil with G equals to 50 kg per centimeter square, let us consider gamma, that is unit weight 1.7 into 10 to the power minus 3 kg per centimeter cube. For G equals to 100 kg per centimeter square, let us assume gamma is 1.8 into 10 to the power minus 3 kg per centimeter cube, and for G equals to 200 kg per centimeter square, let us assume gamma as 2 into 10 to the power minus 3 kg per centimeter cube, which are equivalent to, if you talk about SI unit, this is 17 kilonewton per meter cube, this is 18 kilonewton per meter cube, this is 20 kilonewton per meter cube. So, which are the standard values of unit weight for different stiffness of the soil, which we can consider by looking at their G values. As it is becoming stiffer, the unit weight we have considered or assumed as higher, which is quite justified. Okay. So, now let us start the solution for the vertical mode of vibration first. So, for vertical mode of vibration, the size of the footing is given. So, equivalent radius r naught we can easily calculate, which is nothing but a by pi. So, 75 by 90 centimeter is the area. So, r already we had calculated it earlier. So, 46.35 centimeter, and operating frequency at which we need to find out the displacement amplitude is 1500 rpm, which we had converted to, it gives you omega as 157.08 cycles per second. That also we have seen earlier. Now, we need to calculate using Leismer's simplified analog Bz, vertical mode of vibration. So, Bz we need to calculate. How much is Bz? What is the expression? 1 minus mu by 4 times m by rho r naught cube. which can be written as 1 minus mu by 4 into W by gamma R naught cube. I multiplied this by G, this also by G. So, for 3 different types of soil, we can calculate it like this. Bz for G equals to 50 kg per centimeter square will be 1 minus mu Poisson's ratio is 0.25 by 4. This remains same for all soil. So, you can keep this value constant. What is the total weight of the machine plus foundation system? 0.75 ton. So, see it is 0.25 ton is foundation weight and machine weight is 0.5 ton. So, total is 0.75 ton. So, it can be converted to 750 kg force. So, 1.7 into 10 to the power minus 3 is the value of gamma we have considered, right. And what is R? That is 46.35. So, this is kg force, this is kg force per centimeter cube, this is in centimeter. So, centimeter cube we are getting, that is why finally, we are getting a dimensionless ratio as it is expected. So, let us calculate this and see how much it is coming. 0.831. Similarly, the other two values of Bz also we can calculate. Bz for G equals to 100, the change will be only here, it will become 1.8 as we have considered, all other things remains constant. So, how much we are getting? 0.785, right, and Bz for G equals to 200, that will be 2.0, that is the only change. So, it is coming 0.706. Now, next step, to calculate dimensionless frequency ratio, because now we are handling with the operating frequency. So, we need to calculate A naught. What is the expression for A naught? Omega R naught root over rho by G, isn't it? So, omega R naught root over gamma by capital G small g acceleration due to gravity. Therefore, for 3 different types of soil, we will get 3 values of A naught. A naught for G equals to 50, the first type of soil. How much we will get? Omega is, we have calculated 157.08. R naught is 46.35 centimeter. Gamma for this type of soil is 1.7 into 10 to the power minus 3. G is 50 and small g is 981 centimeter per second square. So, if we calculate this, how much we are getting? 1.355. Okay. For other 2 types of soil, similarly we can calculate. A naught for G equals to 100 is coming how much? In this expression, what are the changes will occur? This remains same, this remains same. This will become 1.8, this will become 100, this remains same. Okay. So, how much A naught we are getting? By calculating, I am getting 0.986. Is it okay? And for the third type of soil, A naught with G equals to 200, what is the value? Again the changes will be here, it will become 2, it will become 200. 0.735. Okay. Now, what is the next parameter we can calculate using this Leismer's simplified analog? Damping ratio. So, damping ratio for vertical mode of vibration, what is the expression? Eta z, that is 0.425 by root over Bz. Bz already we have calculated for 3 different types of soil. So, the eta z for 3 types of soil we can easily calculate. For G equals to 50, it will be 0.425 by root over, how much was the Bz at G equals to 50? 0.831, right. So, how much is damping ratio we are getting? 0.4662. Similarly, eta z for G equals to 100, how much? Bz for 100 was 0.785. So, put here 0.785. Let us see. It is 0.4797, right. And the eta z for third type of soil G equals to 200, Bz for G equals to 200 was 0.706. So, put here 0.706, we will get the value 0.5058. Now, you can note one thing here. The same problem when we have solved using mass spring dashpot model, what was our damping ratio? We assumed as 25%, 0.25, whereas using elastic half space model, using this Leismer's analog, the damping ratios are very high, about close to 50%, means just about the double. Why? Because in mass spring dashpot model, the elastic theory of both soil and machine plus foundation together was not considered effectively. So, that is why the effect of damping ratio which was considered was only for soil, and that was assumed also. Whereas, if we use the elastic half space model of Leismer, in that case it will consider not only the damping ratio of the soil, but the entire system which is vibrating, which I had shown in the dynamic Bushnig's model, that after shifting the load it can be considered as a total system, and the damping ratio of the entire system is considered in this model. So, this is another values of damping ratio which needs to be considered for the design using Leismer's model. Next is, let us calculate the spring constant. Spring constant for vertical mode of vibration is Kz. What is the expression? That is 4 G R naught by 1 minus mu. So, Kz for first type of soil with G equals to 50 is how much? 4 into 50 into R naught is 46.35 divided by 1 minus Poisson's ratio is 0.25. It is coming how much? We had calculated earlier also 12360, so much kg per centimeter. Okay. And Kz for other two types of soil, that is G equals to 100. Only thing, this is linearly proportional. So, it will become 100, it will be double of this. So, 24720 kg per centimeter, and Kz with G equals to 200 will be again double of this. So, 49440, so much kg per centimeter. Now, operating frequency is given to us. What about the natural frequency of the system? that we need to calculate, right. To calculate the displacement amplitude, we should know the frequency ratio. Operating frequency is given. So, let us now calculate the natural frequency. So, natural frequency of the system omega n is nothing but that k z by m. So, k z g by w. Therefore, for 3 different types of soil, omega n with g equals to 50, that will give us how much is k z? We have calculated just now 12360. G is this unit centimeter per second square is 981. W is 750 kg force. How much it is coming? 127.15 cycles per second. Omega n for other 2 types of soil with g equals to 100, we have to put k z for g 100, other 2 things remain same. So, it is coming 179.82 CPS. Am I right? Omega n for g equals to 200 will be k z will change for g equals to 200, other 2 remain same. It is coming 254.3 CPS. Okay. So, with this we will stop our lecture today here. We will continue further in the next class.